Welcome to lecture series on advanced geotechnical engineering being offered by the Department of Civil Engineering, IIT Bombay. We are in module 3, lecture 6 on compressibility consolidation, and we have introduced ourselves to the normally and over consolidated soils, and we have discussed about the methods for determining pre-consolidation pressure. So in this particular lecture we will continue our discussion on normally and over consolidated soils, and then we will try to discuss on over consolidation ratio under consolidated deposits, and thereafter we will try to extend our discussion to the determination of the coefficient of consolidation, the only parameter in the differential equation put forwarded by the Tarjagi's one dimensional consolidation theory. So in the previous lecture we have defined pre-consolidation pressure, and we said that it is the maximum previous maximum effective stress to which the soil has been subjected in the past. So the pre-consolidation pressure is the previous maximum effective stress to which the soil has been subjected in the past. So based on this we can classify predominantly two types, normally consolidated and over consolidated, and there are also some under consolidated deposits, that means that very young deposits. The normally consolidated deposits, soil or normally consolidated soil is actually defined as a soil, and it is called as normally consolidated if the present effective overburden pressure is the maximum to which the soil has ever been subjected, that is sigma dash present is greater than or equal to sigma dash past maximum. And over consolidated soil, a soil is said to be over consolidated if the present effective overburden pressure is less than the maximum to which the soil has ever been subjected in the past. That means that the sigma dash present is less than sigma dash past maximum. That means that in the past the soil would have been subjected to very high the effective stress, and whatever the current stress is very much less than that. So in this case normally consolidated soils are what we have discussed is that these are very prominent in along the Indian peninsula, and along the coastal line the most of the marine clay deposits are normally consolidated in nature. So this becomes a challenge for a geotechnical engineer for designing the structures on these clays. So in the natural condition in the field, a soil either may be normally consolidated or over consolidated, in some cases under consolidated. So soil generally become over consolidated through several reasons, and we have several mechanisms or several reasons. One is that removal of overburden pressure, that means that if a past structure or if a overburden was existing and if that is removed, then there is a possibility that the soil might have actually gone into over consolidated state. And some of the past structures, when they were removed, the soil still experiences or remembers the stress which actually has been subjected in the past. And because of the presence of the large chunks of ice on the soil, and subsequently when it gets undergoes a process of glaciation, then the soil also in the over consolidated state, and either because of the deep pumping or desiccation due to driving, desiccation due to drying, and desiccation due to plant lift of water, and the change in soil structure due to secondary compression, and importantly change in pH of the soil and salt concentration also can change these convert the soil into over consolidated state. And weathering, some ion exchange, and aging of soils, and precipitation of cementing agents, all these things lead to make the soil over consolidated. So in this context, actually whenever possible the pre-consolidation pressure for an over consolidated clay should not be exceeded in construction, and compression will not usually be great if the effective vertical stress remains below the pre-consolidation pressure, and if if the pre-consolidation pressure is exceeded, then the compression will be large. So if for any soil, if the if the loading which is actually is less than that pre-consolidation pressure, the settlements will be small. But if the load actually exceeds to more than the pre-consolidation pressure, then the soil can change into a normally consolidated mode. So in the field, the over consolidation ratio is actually defined as sigma dash C by sigma naught dash sigma dash O. So if OCR is equal to 1, that indicates that normally consolidated soil, and OCR greater than 1 is called over consolidated soils. In fact, OCR is equal to 2, it indicates slightly over consolidated soils, and OCR also can be like 5 and 9, more than 9, and they are heavily over consolidated soils, that means that the clay is very stiff in nature, and the water content is very less, and it has been subjected to very high amount of past very stress in the past. And there are also some cases, particularly it occurs in some lake beds and all, where OCR less than 1. So this is called as under consolidated soil. That is, for example, recently deposited soils either geologically or by man. So the soil has not yet come to the equilibrium under the weight of the overburden load. So the status of this the pore water pressure is soil is that the soil is actually not yet attained the equilibrium under the weight of the overburden above that particular layer on particular point, then pore water pressure would excess of the hydrostatic pressure. The pore water pressure would be excess of the hydrostatic pressure. So these under consolidated deposits are something like very recently deposited soils, either geologically or by man-made activities. So in that case OCR less than 1 is called, but predominantly OCR is equal to 1, it is actually called as normally consolidated soils. Up to OCR is equal to 2, like they are also treated as lightly over consolidated soils, and the OCR value can also go up to 5, 9 and greater than 9, so where they are heavily over consolidated soils. So let us look into some example problems before discussing the methods for determining coefficient of consolidation. So in this example problem, the laboratory consolidation data for an undisturbed clay samples are given, and which is actually given as E1 is equal to 1.1 at sigma 1 dash 95 kilopascals, and E2 is equal to 0.9 at sigma 2 dash is equal to 475 kilopascals. So that sigma 1 minus sigma 2, the sigma 2 minus sigma 1 is the increase in the stress, that is 475 kilopascals minus 95 kilopascals. So what we need to do is that when there is an increase in effective stress, then you can see that the void ratio decreased from 1.1 to 0.9. So the calculate the coefficient of volume compressibility m suffix v, and what will be the void ratio for a pressure of 600 kilopascals. Note that we have to see that sigma dash c is less than 95 kilopascals, that is the soil's pre-consolidation pressure is less than 95 kilopascals. Now the solution runs like this. We have been given the data which is plotted on void ratio on the y-axis and pressure on the logarithmic scale, that is pressure on the sigma dash and logarithmic scale in kilonewton per meter square. And by putting 1.1 for E1 and the point lies here, and for 0.9 the point lies here, that is at 475 kilopascals. Now we can actually determine the slope of this line is delta A by delta sigma, that is delta sigma if it is in arithmetic scale, but coefficient of volume compressibility can be obtained like this, which is nothing but 1 by 1 plus E naught. So here E1 is taken as the initial void ratio, that is 1 by 1 plus 1.1, that is 2.1, then E naught minus E1, that is nothing but E1 is 1.1, E2 is 0.9, and the pressure is that 475 and 95. So with this expression, which is nothing but AV by 1 plus E naught, what we are doing is that AV by 1 plus E naught, and AV is nothing but delta E by delta sigma dash into 1 by E naught. So with this what we have got is that MV we have got. So by getting this MV we can actually after having, so the soil's volume compressibility is known, then in this particular pressure range, then you can actually calculate what is the settlement and all. Similarly, the slope of this E log P curve, the straight line portion of this virgin compression curve is nothing but indicated as compression index. So the slope can be obtained like this: Cc is equal to the slope of line E1 minus E2 divided by log sigma 2 dash minus log sigma 1 dash. So E1 minus V2, so E1 is 1.1 and E2 is 0.9. So 1.1 minus 0.9 divided by log 475 divided by 90. So with this what will happen is that the compression index is actually coming as 0.286, compression index is coming as 0.286. Now as the soil is in the same normally consolidated state, and 600 kilopascals is the right next to 475 kilopascals. So what we wanted to know is that what is the void ratio of a soil at pressure of 600 kilopascals. So for that by taking the same slope, that is Cc is known to us 0.286 and initial void ratio is known to us, that is 1.1. So E3 is required to be found out. So it is nothing but Cc is equal to E1 minus E3 divided by log of sigma 3 dash by sigma 1 dash. Now the sigma 3 dash, which is nothing but that is new pressure, that is 600 kilopascals. So 0.286, that is nothing but E1 is 1.1 minus E3 divided by log of 600 by 95, and Cc is known to us, which is 0.286. So with this what we can actually get is that when the pressure increases to 600 kilopascals at the end of the pressure process of consolidation, what you get is that E3 value is 0.87. Now it decreased further from 0.9 to 0.87. So what we have done in this problem is that the given data is plotted, and then we have determined what is the coefficient of volume compressibility that we have been asked. Then afterwards we determined compression index from the given data, and then we were asked to find out what is the void ratio of a same soil with undergoing the consolidation, then what is the void void ratio at a pressure of 600 kilopascals. So that works out to be 0.87. From the given data, from this portion belongs to lecture 5 of module 3. From the given data of pressure versus void ratio, we have to plot E log P curve and logarithmic of pressure on the x axis and void ratio on the y axis. And once we get these plots, we have to identify a point where the maximum curvature prevails, and from there we have to draw an horizontal line, and then a tangent need to be drawn from that point of where the maximum curvature exists, and we need to bisect this line, bisect this angle. Let us say if that angle is say delta alpha, that angle need to be bisected, and then from this point D a line need to be drawn, and this tangent, which is the straight line portion of the virgin compression curve, need to be extended, and the point where it actually meets that bisected line, and from there we can actually draw, and that point is regarded as pre-consolidation pressure according to Casagrande's method. So in this particular problem, from the given data, what we have done is that we took point D, and then we have drawn horizontal line, and from the point D we have drawn a tangent, forward tangent, and then we bisected that angle, and then we have drawn a line through point D, and then we extended this back tangent from the straight line portion of the virgin compression curve, and the point where it meets, that is actually regarded as pre-consolidation pressure. In this problem we have got as 117.5 kilopascals. Then what we did is that we determined the pre-consolidation pressure from the E log P plot. So here at P2 500 kilopascals, E2 is 0.8 and P1 300 kilonewton per meter square, E1 is 0.9. So the pre-consolidation pressure is works out to be 117.5 kilopascals. Now from the compression index we can actually find out here E1 minus E2 by log of P2 by P1. So 0.9 minus 0.8 by logarithmic of 500 by 300, you will get a compression index of 0.451. So the compression index is actually obtained from the for the given data as 0.451. Now after having discussed about these problems, now we said that we will try to look into the methods for determining coefficient of consolidation. And we have been introduced ourselves about the coefficient of consolidation term for the first time in the consolidation and compressibility module in the consolidation equation, wherein we said that dou u by dou t is equal to Cv dou square u by dou z square. So the Cv term is the coefficient of consolidation. So the coefficient of consolidation Cv is the only term in the consolidation equation that takes into account the soil properties which govern the rate of consolidation. So the Cv is the only term, or you can say that soil mechanics term in the consolidation equation and which govern the rate of consolidation. So the coefficient of consolidation Cv signifies the rate at which the saturated clay undergoes one dimensional consolidation when subjected to an increase in pressure. So one more physical significance of coefficient of consolidation is that it signifies the rate at which the saturated clay undergoes one dimensional consolidation when subjected to an increase in pressure. So a knowledge of Cv is essential for predicting the rate of primary consolidation settlement. So the knowledge of from the consolidation test data, there are methods which are actually there also in the laboratory as the methods are also there in the field also. Particularly when you have got a soils which are isotropic, then it is assumed that horizontal consolidation as well as the vertical consolidation they are same. But if the soils are say anisotropic in nature, then the horizontal coefficient of consolidation, vertical coefficient of consolidation, they are different. So naturally for CH, that horizontal coefficient of consolidation is actually more than Cv. That means that this is analogous to when we discussed the permeability, the horizontal permeability in the horizontal direction is actually greater than permeability in the vertical direction. So at that time we have discussed that the ease with which the water can flow through the soils is actually less in the horizontal plane than in the vertical plane. The reason what we discussed is that as the sigma h is equal to k naught into sigma v, at k naught is the coefficient of earth pressure at rest. Because of that, because of the less horizontal stress, so the less you can say that less confinement. So because of that, the coefficient of permeability in the horizontal direction is actually more than in the vertical direction. As permeability and coefficient of consolidation are related, we based on the same analogy we can also say that the coefficient of consolidation in the horizontal direction is actually will be more than the coefficient of consolidation in the vertical direction. So the coefficient of consolidation basically signifies at which the saturated clay undergoes one dimensional consolidation when subjected to the rate at which a saturated clay undergoes a one dimensional consolidation when subjected to an increased pressure. So for isotropic cases where identical properties are there, then we can take Cv is equal to Ch. So knowledge of Cv is essential for predicting the rate of primary consolidation settlements. There are also the field methods are there for determining coefficient of consolidation by using piezo cones. One can actually determine the the coefficient of consolidation in the field. So there are several methods available for obtaining coefficient of consolidation over a period of from 1940 onwards. The number of methods have been evolved, and these methods compare the characteristic features of theoretical time factor T or TV and the degree of consolidation U relationship with time compression data obtained from the laboratory. So from the whatever the data we obtained from the laboratory, so what people compare is that the U versus TV or U versus T curves data are compared. So these methods compare in principle characteristic features of the theoretical time factor TV and the degree of consolidation U relationship with time compression data obtained in the laboratory. So the square root of time fitting method, which is also called as root T method, proposed by Taylor 1948, and the logarithmic of time fitting method, that is log T method, and also called as Casagrande's method, which is after Casagrande and Fadum 1940, are the most widely used methods in practice and are considered as standard methods. So we have two broadly classified methods, and one is root T method, which was put forward by Taylor in 1948, and log T method, which is called as the Casagrande's method, and which was put forward by Casagrande and Fadum 1940, and both these are the most widely used methods in practice and are considered as the standard methods. So we will discuss these two methods, and then also some couple of methods we will discuss which are actually evolved in the recent literature. So for determining the coefficient of consolidation by using the root T method, so first let us consider the root T method. In the root 2 method, the CV values are larger than those obtained from the Casagrande's method. So the reason we will actually discuss, but what we need to understand is that we have to plot the dial gauge readings for the specimen deformation for a given load increment. That means that we know that we have discussed that in the consolidation or iodometer test, each load will be kept for about 24 hours, and let us say that if you are keeping 100 kilopascals load, and the next load increment is 200 kilopascals. So each load increment is kept for about 24 hours at a given definite time, and so for a given load increment, whatever the time versus compression data, which is the dial gauge readings, the beginning of the placement of this load and till the end of this load, and time has to be plotted on the semi logarithmic graph paper. Now what we need to do is that we have to plot 2 points A and B on the upper portion of the consolidation curve, which corresponded to time T1 and T2 respectively. Note that T2 is equal to 4T1. So this is nothing but we have to plot 2 points on the consolidation curve. So this is dial gauge readings on y axis and the logarithmic of the time in minutes on the x axis, and this is a semi log curve, and this is the U versus log TV, that is U versus TV or U versus T theoretical curve, wherein you can see that where this is the 0% consolidation, and somewhere here when you extend this portion is into the secondary consolidation after the end of primary consolidation. So this 90% consolidation or 0.9 is somewhere here, and this portion is in this, so this is elaborated one with the time versus deformation is actually shown here. So you can see that the important part of this method is that we have to plot 2 points A and B on the upper portion of the consolidation curve. So the upper portion of the consolidation curve means somewhere here, and where the curvature is actually changing from the beginning portion, you can say that 2 points have to be put such a way that the upper portion of the curve such a way that which correspond to time T1 and T2. So note that T2 is equal to 4T1. So the difference in times the T1 and T2, so T2 is equal to 4T1. With that we have to identify 2 points. So after having done that, the difference in dial readings between A and B is equal to x, and so we have to locate point R, which is at a distance x above the point A. So what we need to do is that the difference in dial gauge readings is x here. Let us say that if these two the dial gauge vertical compression readings between A and B is say some x, and above some x again a locate point R, that means that another this is one x and this is the another x. So here what you see, some initial compression, some primary consolidation region, and this is the secondary compression and secondary consolidation region. So locate point R. So we have located point R above A, which is x units above the x units vertically above this one, and that from through this point draw an horizontal line and you indicate that as the D naught, that is the dial gauge reading at 0% consolidation. Take that as the dial gauge reading at 0% consolidation D0, and this is regarded as D0 at 0% consolidation. After obtaining that, draw the horizontal line RS, and the dial reading corresponding to the this line is D0, which we have already said, and which correspond to 0% consolidation. Then what we do is that the project the straight line portion of the primary consolidation curve and secondary consolidation curve and intersect at T. Then the dial reading corresponding to T is D100, that is 100% consolidation. So what we need to do is that the secondary consolidation portion and primary consolidation portion, this tangent we have to extend further like this, and this tangent we have to extend backward, and this point when you take it back, and this is the point what we indicate is that for that given load increment, this point is the dial gauge reading corresponding to 100% primary consolidation, that is at the end of 100% primary consolidation. So beyond this it is actually entering into the secondary consolidation and secondary compression zone. So this D100 is nothing but which is at the end of primary consolidation, D0 at the 0% primary consolidation. The average of primary initial beginning of the primary consolidation at the end of the primary consolidation is called as D50, which is nothing but D0 plus D10 by T, and the time corresponding to D50 is regarded as T50. Okay. So note here the D50 is equal to D0 plus D100 by 2, and the time corresponding to the D50 is regarded as T50. So this line indicates that, which is extended towards, for example in this case it is 10.2 minutes. So we need to determine the point V on the consolidation curve such that the reading correspond to a dial reading of D0 plus D100 by 2, which is equal to D50. The time corresponding to point V is called the T50, that is time for 50% consolidation curve. So in order to determine CV from the equation, what we need to do is that for 50% consolidation TV is nothing but 0.197. So by using TCV by H square, and H is nothing but H drainage square, that is H is nothing but the depending upon the drainage. For example, in case of consolidation test we have got this filter stone both top and bottom, so it is HDR by 2. So we can write CV is equal to 0.197, that is the time factor for 50% consolidation into H square divided by T50. So from the graph what we do is that we actually simply measure what is T50. Once we get that one, we can calculate by knowing the thickness of sample divided by 2 in case of double drainage, we can get the CV value. So as for example here for D50, let us say for D50 that let us say the time here is shown as 10.2 minutes. So CV can be obtained as 0.197 into 2.06 by 2, that is nothing but this is thickness of the sample divided by 2 whole square divided by 10.2 into 60, then we will get the coefficient of consolidation in centimeter square per minute. So in the logarithmic time method, what we have done is that for a given load increment, dial gauge readings versus logarithmic of time we have to plot, and then what we need to do is that we have to indicate 2 points, mark 2 points on the the dial gauge reading log T curve, and such that T2 T1 is at A or T2 is at B, let us say, and T2 is equal to 4 T1, and that is the time lag difference, and then that the vertical dial gauge reading difference between A and B points is, say, let us say x, then with another distance x above locate a point R and then draw line RS through that, and the point along that particular line where it meets to the dial gauge reading, it indicates that D0, and then when we are extending the end of primary consolidation tangent and then the straight line portion of the primary consolidation portion and the secondary consolidation portion when they meet at point T, and this is actually is indicated or regarded as D100, and D50 is equal to D0 plus D10, and with that we can actually locate a point D50 here on if that point is B, when we drop a vertical, that is the T50. So with that what we can actually get is, the by knowing T50 we can actually calculate for 50% degree of consolidation, TV is equal to 0.197. So with that we can actually get what is the the so called coefficient of consolidation. The next method is Taylor's root time method. Here what we need to do is that this is also for a given load increment, plot the dial reading and the corresponding square root of time. So here dial reading on the y axis, and on the x axis square root of time is actually required to be plotted. Then we have to draw the tangent dq to the early portion of the plot. So here in this particular this is the Taylor's root time method. So you can see that the x axis is actually is marked with a root t, that is in minutes, root t which is in minutes. So whatever the time which we take, that we have to plot it in the root t scale on the x axis, and the dial gauge readings whatever we record we can actually plot here. So in this one assumption is that the initial portion is actually assumed to be a straight line. So normally for certain soils where the secondary consolidation or clay soils, the getting this straight line portion is difficult, but in the presumption with where if the organic pattern is say not prevalent, if the soil is actually silty in nature, there can be possibility that the straight line portion can be obtained. So in this case we can actually draw a line, a tangent such a way that passing through the initial portion of the curve which is the straight line portion, draw a line which is actually is dq is here. Okay. So this is what the dq is mentioned, draw the tangent dq to the early portion of the plot and draw the line dr such that OR is equal to 1.15 OQ. So we will see how OR is equal to, this is O, and if this is O here, OR is equal to 1.15 OQ, that means that OR is equal to 1.15 OQ. So this is we draw the initial portion, the dq, and another line which actually originates from D again, which is the R here. So how this has been obtained is that if you look into this theoretical curve where u versus root TV, again we said that this is analogous to u and TV and u and root TV and u and the settlement or compression versus root T. So these two are analogous. So because of this what we do is that this u and the root to v, the nature of the curve is like this. So this is 0% consolidation and this is 90% consolidation. So this vertical height difference is 0.9 and this is 1. So this triangle has this ordinate is 0.9, this ordinate is 1. So here the upper part of the u versus root to v is almost a straight line. You can see that the upper part of the u versus TV is almost straight line. This is for this is based on TV is equal to pi by 4 u by 100 whole square. So by using that one we can actually say that this slope of this line is nothing but 2 by root pi. The slope of this line is nothing but 2 by root pi. So with this what we can actually obtain now is like this. The slope of this straight line portion of this u versus root to v is 2 by root pi. This is actually obtained from for primary consolidation equation for u less than 60%. We said that u is equal to p by 4 u by 100, pi by 4 u by 100 whole square. So that one when you simplify we will actually get 2 by root pi as the slope. Okay. So now for the straight line portion, so we can write that AC is nothing but AC is nothing but that is here for 90% consolidation, AC is nothing but root 2V is nothing but 80% for 90% consolidation time factor is 0.848. So which is root over 0.848, and AB is nothing but vertical ordinate, this triangle, if you look into that OAB, then OA is equal to 0.9 and the slope is 2 by root pi, then AB becomes 0.9 into 2 by root pi. So with that what we will get is that AC by AB is obtained as AC by AB is nothing but root over 0.848 divided by 0.9 into 2 by root pi, which once we simplify we will get AC by AB as 1.15. That means that the theoretical curve U versus root 2V is a straight line up to 60% consolidation, and the abscess of the curve of 90% consolidation is 1.15 times the extension of an absence of an extension of the straight line. So the theoretical curve U versus root 2V is a straight line up to 60% consolidation, and the abscess of the curve at 90% consolidation is 1.15 times the abscissa of an extension of the straight line. So using this logic, what we have said is that the OR is such that OR is equal to 1.15 times UQ is actually considering the analogy, and then by using the characteristic of U versus root 2V, we can say that OR is equal to 1.15 Q can be set. Once we get that, once we draw this particular these two lines, the abscissa of the point E, that is the intersection of dr and the consolidation curve, will give you root T90, that is the square root of the time for the 90% consolidation. That is that point where this dr will intersect the consolidation curve, that is this point. That is, this point is actually regarded as E, and the vertical when you drop we get is the time required for 90% consolidation. So this is 90% consolidation, this is 100% consolidation, and this is regarded as the 0%. This point D is regarded as the 0% consolidation, that is the dial is reading at 0% consolidation. So the value of the T for UV is 90% is 0.848. So CV can be obtained as 0.848 into h square by T90. So here also in this thing, H is depending upon the drainage path, single drainage or double drainage, and based on that we can actually calculate CV, and which is nothing but 0.848 into h square by T90. So this is was discussed already. So with that method, by using that procedure which we have discussed in the Taylor's root T method, we can actually find out what is the the degree, the quotient of consolidation. And if you look into the chief differences between these two methods, and log time method makes use of early pre-consolidation, makes use of early primary consolidation and the latter time responses, that is secondary compression, and in comparison the root time method only utilizes early time response, which is expected to be a straight line. So log time method makes use of early as well as lateral time responses, but in comparison root time method only uses the initial portion of the consolidation, and which is assumed to be a straight line. And root time method should give good results except with non-linearity problems arising from the secondary compression caused substantial deviations from the expected straight lines. So if there is a secondary consolidation situations when they are actually happening, then the root time method will not be able to give the good results, because the basic problem is that the non-linearity which actually arises because of the secondary compression. So most pronounced for clay soils with organic, so this is this non-linearity is actually pronounced, and of the dial gauge reading versus root T curve or U versus root TV curve is actually tend to be non-linear, and the straight line portion may not be expected. So that is for marine clays. So basically we can actually we can put like that, as logarithmic time method says for primary consolidation, and it takes into consideration lateral time response, that is secondary consolidation. We can say that the log time method is most suited for clays, especially marine clays, and root time method is for silts, and where the organic matter is even for organic silts it is a question, but if it is an absence of organic matter, then there can be considered. So, log time method is actually most suited for clays, and root time method can be said as the most suited for silts. And in the recent past, then there are other methods which are actually have come. They are called early stage log T method, and these methods, this is one of these recent methods. This was actually put forward by Robinson and Alam in 1996, and this is an extension of logarithmic time method, and the early stage of the logarithmic time method. So here what they have done is that the early stages of, so this is, you can say that this the logarithmic time method was actually extended by this Robinson and Alam in 1996. This was done basically by looking into the field data, where the quotient of consolidation equations, quotient of consolidation values are very high when compared to the laboratory data. So, the early stage of log T method, that is after Robinson and Alam 1996, this is an extension of the logarithmic time method and is based on the specimen deformation against the logarithmic of time plot. So, in the first step, they follow the logarithmic of time method to determine D naught. So, here also to determine D naught, we have to follow the procedure which we adopted. So, what we have to do is that we have to we have to first plot the dial gauge reading versus the logarithmic of time. Then we have to plot and indicate 2 points such a way that A and B, and such a way that the vertical compression difference is say x, and the horizontally on horizontal axis, these points A and B are located such a that TB minus TA, TB is equal to 4 times TA, and then we can actually determine D naught, which is corresponding to 0% primary consolidation. Then what we do is that draw the horizontal line DE through the this D naught point corresponding to the 0% consolidation, and then they draw a tangent through a point of inflection, that is through the point of inflection where the straight line portion is there, and beyond which actually there is the secondary consolidation, that is the 100%, 90% consolidation and 100% consolidation will actually come here. So, extend this tangent like this, and the point where this meets this horizontal line DE is indicated as G. So, this particular point is regarded as the tangent intersects the line DE at G. So, this tangent intersects the line DE at G, and then determine T time T corresponding to G, which is the time at UAV is equal to 22.4%. That is this is the time which correspond to UAV is equal to 22.4%. For 22.4% consolidation, the time factor is TV is equal to 0.0385. So, by using this, and we can actually calculate CV, which is nothing but 0.0385 HDR square divided by the time for 22.14% consolidation. So, with this what we can actually get is that we will get the by using the early stage of logarithmic either the consolidation test for a given load increment, we can calculate the consolidation, we can calculate the quotient of consolidation, and we need not actually wait for the consolidation test to complete. As for a given load increment, as the data starts coming, and we will be able to plot and then try to get the quotient of consolidation from the early part of consolidation itself. So, in most cases for a given soil and pressure range, the magnitude of CV determined using logarithmic of time method provides the lowest value. The highest value is obtained from early stage of the logarithmic time method. So, this is because for a given soil and pressure range, the magnitude of CV determined using logarithmic of time method provides the lowest value, and this is the highest value is obtained by the early stage of logarithmic. So, if you compare with the conventional logarithmic time method, the early stage log t method value is on the higher side. The reason is that this is because the early stage of logarithmic time method uses the earlier part of the consolidation, whereas the logarithmic time method uses the initial as well as the lower portion. That is the lower portion where the component of secondary consolidation also comes into picture. So, because of this, the the early stage logarithmic method, log t method, will actually has higher values, predicted values are on the higher side. And when the lower portion of the consolidation curve is taken into consideration, the effect of secondary consolidation plays a role in the magnitude of CV. So, several investigations have also reported that CV value obtained from the field is substantially higher than that obtained from the laboratory test conducted using conventional testing methods, that is logarithmic of time and square root of time method. So, use of early stage logarithmic time method may provide a more realistic values of the field. That means that what this author's contention is that by using this early stage logarithmic of time method, it may give us a realistic values which may match with the field values. So, when the lower portion of the consolidation curve is taken into consideration, the effect of the secondary consolidation plays a role, and because of that the magnitude of CV decreases. So, several investigators also reported that the CV value obtained from the field is substantially higher than that obtained from the laboratory tests conducted using conventional testing methods like logarithmic of time and square root of time method. And by adopting this early stage logarithmic time method, the values may provide have a good match with the realistic values in the measured in the field. So, after having discussed this methods for determining coefficient of consolidation, let us look into what we have done is that in the determination of methods for consolidation, we have discussed about the two standard methods and one early stage method which is given by Robinson and Alam in 1996. Now, let us consider one example problem wherein the problem statement works out like this. We have got 8 meter depth of sand overlies a 6 meter layer of clay below which is an impermeable stratum. The water table is 2 meters below the surface of sand, and over a period of 1 year a 3 meter depth of the fill is to be dumped on the surface over an extensive area. That means that the fill extends to large areas. The saturated unit weight of the sand is 19 kilonewton per meter cube and that of the clay is 20 kilonewton per meter cube, and above the water table the unit weight of the sand is 17 kilonewton per meter cube. So, for the clay, the relationship between the void ratio and the effective stress in kilonewton per meter square can be represented by the equation which is given in the problem statement as E is equal to 0.88 minus 0.32 logarithmic of sigma dash by 100. So, here we have the 8 meter depth of the sand overlies a 6 meter layer of clay, and below which there is the surface water table is 2 meter below the surface of the sand, and here if you notice here the fill is actually not dumped over a instantaneously, it is dumped over a period of 1 year. So, the construction period takes about 1 year for the fill to reach about they maintained about 1 year to reach a 3 meter height on the soil strata which is actually given, and the saturated unit weight of the sand is 19 kilonewton per meter cube and that of the clay is 20 kilonewton per meter cube, and the unit weight of the soil above the water table of the sand is 17 kilonewton per meter cube. And then here if you look into this, the relationship between the void ratio and the effective stress are given. That relationship is actually worked out from which is obtained from E log sigma or E log P curve, which is nothing but E is equal to 0.88 minus 0.32 into log sigma dash by 100, where the sigma dash is measured in kilonewton per meter square. And it is also given that coefficient of consolidation of this soil is 1.26 meter square per year. We know that the coefficient of consolidation, the unit weight is meter square per units are meters per second, meter square per year or centimeter square per minute. This is the units are the coefficient of consolidation of this soil in the clay is 1.26 meter square per year. So, what we need to do is that calculate the final settlement of the area due to the consolidation of the clay and the settlement after a period of 3 years from the start of dumping. So, we need to calculate the final settlement of the area due to the consolidation of the clay and the settlement after a period of 3 years from the start of dumping. Then if we are actually having a very thin layer of sand freely draining type and existed 1.5 meter above the bottom of the clay layer, then what would be the value of final and 3 year settlements. So, first is that clay is homogeneous, but naturally there are some lengths of the clay and where which actually has been located. Generally this when you have got some clay deposits, they are stratified in nature, and sometimes there is a possibility that large thin sand lenses can actually come. Suppose if these thin sand layers are not located from the soil investigation, and if the settlements are actually estimated without considering this presence of this thin sand layer, then the settlements will be catastrophic in nature. That is what actually we are going to demonstrate through this problem. So, here if a thin layer of sand and a freely draining type and existed 1.5 meter above the bottom of the clay layer, then what would be the values of the final and 3 year settlements. So, the strata which is actually given, the problem is explained here. Bottom layer is impermeable and the upper layer is here is sand. So, 8 meter layer is sand here, and water table is 2 meter below the ground surface, 2 meter below the ground surface, and we can see that here the clay is 6 meter thick, and the second portion what we have is that this we have got impermeable layer, but a thin layer of sand is actually shown here. So, this is 4.5 meter, this is 1.5 meter, so this is a 1.5 meter below the base layer, and this is the homogeneous layer. So, since the fill covers the wide area, the problem can be considered to be one dimensional. The consolidation settlement will be calculated in terms of Cc, considering the clay layer as a whole layer, and therefore the initial and final values of effective vertical stress at the center of the clay layer are required. So, we can actually calculate sigma naught dash that is at this center of this layer. We know that because here the excess pore water pressure dissipated is minimal here. So, we calculate at the center of the clay layer sigma naught dash. So, this is actually sigma naught dash is equal to 17 into 2, that is above water table, 9.2 into 6 plus 10.2 into 3. So, this is sigma naught dash, that is taking pore water pressure out of it. Then E naught, which is 0.88 minus 0.32 into log 1.198, because here sigma naught dash is 119.8 divided by 100, we will get this much. Then what we have is that E naught initial void ratio from the E log P data is 0.855, and sigma 1 dash, because here we wanted to say that 119.8 plus 3 into 20. So, this actually has been loaded over a period of 3 years. So, the sigma 1 dash is 179.8 kilon per meter square. So, the logarithmic of 179.8 divided by 119.8, which is 0.176. So, with that what we get is that the settlement is about 182 mm. So, in this particular problem we will actually stop here, wherein we actually discussed about how we can actually determine the final consolidation settlement, and this is the part of the problem only, wherein we have calculated the the settlement which is coming out as, if this clay undergoes consolidation, the total settlement is a consolidation settlement will be 182 mm. And then further we actually have to account for, if you notice that the time required for filling the placing the fill on the soil is about 1 year. So, then we have to do correction for the construction period correction. Once this construction period correction concept is introduced, then we will try to solve the part 2 of this problem, and then we will try to take into the effect of say thin naturally occurring thin layer of sand and how that affects in accelerating the consolidation. Generally, if this is one of the classical example. Sometimes if it is not recognized during the site investigation, if the structure is constructed thinking that the soil is homogeneous and free from these lenses of sand layers, and if it is freely draining type, the settlements can be the catastrophic in nature.